Kia ora, good evening, and hello everybody in my physics class and other physics classes who might be interested in looking at what we're doing here. I just need to move us along a little slot here. The plan of attack is to look at a proof of this equation which is given on the formula sheet. I'll just make myself a little pretend mouse pointer here. Here we go. Look at this thing here. So that's the formula we want to prove. And I'm doing this on the 28th of March 2022. This formula is given in the resource booklet for NCEA 3 Physics, and it's not okay just to be given these things from on high and just believe in them. It's nice to know where they come from. So we start with a reference circle, like I did in an earlier video on velocity and simple harmonic motion, even using some of the same graphics. Reference circle there, horizontal there. This is the angle that we've got at the moment. We're looking at it. There it is there, theta is omega t. And there's the angle, and then we have our simple harmonic motion oscillator bobbing up and down on the line, on that line there. We have the circular motion one there. Now in this case, we're looking at the acceleration in simple harmonic motion, which is always opposite to the direction of the displacement. If it's anything is displaced this way, the acceleration is that way. Part of the definition of simple harmonic motion. It is actually a component of the centripetal acceleration of the reference circle device that we've got. Now, if we look at these two vectors, pull these two vectors out, look at them like that, then we need to flip the SHM vector because in this particular case, we've drawn it above the line with a positive value, even though we know it's going down. So if we flip it and change its sign, and then draw it upwards. Centripetal acceleration always towards the center, it's always positive, so it doesn't really matter. But the simple harmonic motion acceleration, if it's pointing up, has to have a negative. Then we can use the form a right triangle with a base, put a right angle triangle in there, and we can then show the angle, theta is omega t. Start the trigonometry, which is the sine of that angle is equal to the opposite over the hypotenuse, negative AS over AC. Swap the sides of the new equation, like that. Very, very complicated step, we can handle it. Multiply both sides of the equation by AC, and you finish up with AS is negative AC, sine omega t, which makes sense. If the sine is 0, there's no acceleration, because the angle is 0. If the sine is whatever the sign is 1, then we get the maximum acceleration back towards the center. But we remember that for circular motion, the centripetal acceleration is v squared upon r. And then I'm going to multiply that, v squared upon r, by 1. But it's a special 1. It's r squared divided by r squared. That's still 1. So I can then multiply that in, and if you look at that, if you pause the video, you'll see that v squared upon r times r squared divided by r squared is v squared over r squared times r, which is kind of cool. Okay, that's neat. Now remember that v upon r is omega, so v squared upon r squared is omega squared. We also know for simple harmonic motion that the radius of the reference circle is equal to the amplitude of the motion. So we change r to an a. Let's set this new expression for the centripetal acceleration off to one side, and then we put that into the AC at the top. Copy the equation down, and there's AC in red, and those two places, and we plonk omega squared a into there. Now that is on the formula sheet in the exam. However, you can tell by the space at the bottom that there's more, but wait, there's more. And if I do something cheap and nasty like on some late night infomercial, I could even point, but wait, there's more. Right, here we go. Remember the definition of simple harmonic motion? That the acceleration is proportional to and opposite in direction from the displacement. In other words, it's negative 1 times some positive number. So it's proportional to, not the same size, but proportional to, but opposite of from. So it's negative of a positive number times the displacement. Well, let's copy and recolor a new equation. like that, and do the A sine omega t as a special feature. And we remember that A sine omega t is equal to y. That was what the displacement is. So we can then put y in there. Now this is cool because omega squared, look at the top bit there, omega squared will always be positive. Put a negative in front of it, we get acceleration is equal to -1 times a positive number times the displacement. So our equations fit the simple harmonic motion rules. They're not the only ones, there are other equations, but these are the ones that we tend to use in SHM and NCEA 3. Other ones can be seen too. Thank you very much for looking. I'll go back to that. I hope this has been useful. Cheers all.